Hi, my name is Junxiao Shi. Today I'm presenting my personal project, NDNTS, NDN Libraries for the Modern Web. NDNTS is a set of modern JavaScript libraries. You can use it in both TypeScript and JavaScript projects. NDNTS works in Node.js and modern browser environments. It has more than 90% of test coverage, and I have automated and manual browser testing on desktop, Android, and iOS. NDNTS can operate standalone without a forwarder, or if you choose, you can connect to NFD or NDN DPDK forwarder. Most importantly, NDNTS is actively maintained. New features are being added monthly, and we support the latest NDN specifications. In this demo session, I will show some code samples of the endpoint abstraction in NDNTS, which is a better version of Face. Compared to Face, it can automatically handle interest retransmission, data signing verification, data buffering, and transport error handling so that your application does not have to. I will show some code samples for the trust schema. It is inspired by Casey Nichols' versatile security toolkit presentation, but now I have actual implementation in the NDNTS libraries. I will show an online web application that displays the NLSR routing status on the NDN testbed. NDNTS contains a partial implementation of the NDNCERT protocol. I will show a demo of the NDNTS Personal Certificate Authority application as well as a command line NDNCERT client. I will show a new version of HomeCam, the home surveillance camera web application. I demoed this in NDN Community Meeting 2018, but now I have rebuilt it with NDNTS and added the Screencast feature. Endpoint is a new API introduced by NDNTS. It is a better version of the Face that you may be familiar with. In other libraries, the bottom layer is the transport. Usually it's a connection to NFD. Then there is a Face. The Face handles interest data matching and prefix registration. And then your application talks to the Face. You can express interest or you can register a prefix. But if the transport has some errors, if the interest times out, you need a retransmission. You need to send the data or verify the data, or you need to use the in-memory storage. It's on your own. The application has to manually handle those. But in the case of NDNTS, first is we can make use of multiple transports. So it's multiple uplinks. So for example, in the browser, you can connect to multiple testbed routers. And if those transports has a socket error, it will be reconnected automatically. Your application doesn't need to worry about that. Currently, we support UDP, TCP, Unix WebSocket. We also support web Bluetooth, so you can directly talk to a Bluetooth device from your browser. Then built on top of the transports, we have the packet demultiplexer, which internally can forward the packet between endpoints and the transports. Then within the endpoint, a lot of features are already implemented. On the consumer side, there is automatic interest retransmission, which I will show later. There is data verification, which is based on trust schemas. And we also plan to have schema-based decryption. On the producer side, of course, we have prefix announcement or prefix registration. Then we have a data buffering, which I will show later. There is a trust schema-based data signing, and also and we also plan to have a schema-based encryption feature. And with all those handled in the endpoint and the lower layers, your application can just focus on the application logic. As you may already know, NDN network provides a best effort data retrieval service. When your application expresses an interest but it does not get satisfied, you are responsible to retransmit the interest periodically. Usually you follow this flowchart. You first prepare the interest, set the name and other field. You call face.expressInterest. It will let you set a few callbacks. The onData callback is invoked when the data comes back. You can use the data packet. OnNeck and OnTimeout callbacks means the data does not come back. In that case, you will maintain a counter, how many times the packet interest has been retransmitted. If it does not exceed the retransmission limit, you will compute exponential backoff duration. After that backoff, you express the interest again. If the retransmission limit has exceeded, you will handle the error. The data cannot be retrieved. In other libraries, you have to implement this flowchart manually, but in NDNTS, this is built in. You can enable interest retransmission. Here you call endpoint.consume, give it the interest. Then you just say, oh, I want 2 retransmissions. Everything else is more automatic. If within the retransmission limit, the data comes back, you can use it. Otherwise, you get an error and you do error handling. Another feature of Endpoint is data buffering on the producer side. The use case is when the first interest for segment 0 arrives, your producer can prepare the data packets for all the segments and put them into the data buffer so that subsequent interests can be satisfied from the buffer automatically. In this example code, we make a producer for /prefix. When the interest comes in, if it satisfies certain condition, we generate all the segment. Then we call data buffer.insert. We give it all the data packets. When subsequent interest comes in, the endpoint will automatically check the data buffer. If the interest can be satisfied by the data buffer, then the handler function does not get invoked again. In other libraries, you can achieve that with in-memory storage, but the developer must query the in-memory storage for every interest manually. In NDN Community Meeting 2019, Cassie Nichols presented her work on the distributed network measurement protocol. An interesting part of her presentation is the versatile security toolkit, and most notably, an easy-to-understand syntax to define trust schema. So using that syntax, I wrote the trust schema. This particular schema is coming from in this schematized trust paper. It defines how to send the packets in a web blog system. So there is a root key which sends the admin certificate, which sends the author key, which then sends the article packets. But following the prior work, the trust schema has 2 parts: the policy and a set of trust anchor certificate. Within the policies, there are some patterns to define the name structure, such as how to name the article data packet. There are also rules that says who can send what. This line is the rules. In NDNTS, we can construct a trust schema from the policy imported from that syntax and from the trust anchor certificates. Then, from the schema and a keychain, the local keychain, we can construct a trust schema signer. So in this code sample, suppose the keychain already contains the admin key and the author key. Then we want to sign the article data packet. We create that data packet and say trust schema signer.sign that data. The schema will automatically select the author key and not the admin key, because according to the trust rules, the article should be signed by the author. But if we try to sign some other data set is not an article that does not match the rules, does not match the policy, then the signing operation will fail because the trust schema says this packet cannot be signed. My future work is I want to be able to automatically generate or request a new certificate. For example, suppose the keychain started with only the admin key, there is no author key, and we want to sign the article data. Then the trust schema signer could automatically generate the author key according to the name patterns. The other side of trust schema support is the trust schema verifier, which verifies packets according to the trust schema. To use that, we can construct a trust schema verifier from the schema itself, an endpoint to access the network, and a local keychain if you want to use your own certificate in the schema. Then you can call verifier.verify, give it the data packet. It will throw an exception if the data cannot be verified. The trust schema verifier can be easily integrated with the endpoint. When you say endpoint.consume the interest, you can pass it the verifier instance. If so, it will automatically verify the retrieved data packet. I think the trust schema worker has a lot of potential. In the future, we can potentially schematize everything. In current libraries, the APIs are fragmented. You use a keychain to sign the packets. You use validator config to verify the packets. You have the name-based access control library to encrypt the packets. Then there is also a RDR metadata to do version discovery. There is a flick manifest to index segmented object. But in the future, NDNTs want to have a coherent API based on a JSON-based schema, which is an extension of the schema you saw earlier. So within that schema, we find a pattern that matches a name. Then in the policy rules, it can determine how to compress the packet, how to segment the packet. Do you use index segmentation or do you use byte offsets? How to encrypt the packet, and also the signing key, which we already have now. And I also plan to work on an NDNTs name designer web application. It will allow you to visually design name structures and designate policies to each name pattern. Next up is an online demo of the NLSR status on NDN Testbed web application. You can access it at nlsr-status.ndn.today. You can go to this website now. It will connect to the NDN testbed using NDN find closest hub service. Then it retrieves LSDB routing information dataset from the NLSR routing daemon. It can decode the LSDB using NDNTS Evolvability-Aware TLV Decoder. I will show a code demo later. And finally, it renders the routing information on a pre-act web application. This is how it looks, but if you go to that website, you can see it live. As I mentioned, the Evolvability-Aware TLV Decoder, this makes it a lot simpler to write applications that deal with TLV structures. As a simple example, NLSR has a LSA-info structure. It has the TLV type, TLV length, a name, a sequence number element, and an expiration time element. With NDNTs, you can decode this structure in just 7 lines. I'm only showing 4 deals. The core logic. You construct an evolvability-aware decoder with the top-level TLV type. Then you specify the decoding rules of the 3 sub-elements: the name, the sequence number, the expiration period, and how to decode them as in function calls. But if you try to do the same in NDNCX, I go to read NLSR code. They have the decoder there, 23 lines, and it doesn't even support evolvability. It's a lot more complicated. NDNTs contain a partial implementation of the NDN certificate management protocol, both in API and as command line tools. On the certificate authority side, we support the CA profile packet, a basic certificate issuance workflow, and the pin challenge. There is no probe command or other challenge for now. Then the command line tool also supports the same basic issuance workflow, the pin challenge. It can not only manage NDNTS keychain, it can also integrate with the NDNCXX keychain. So you can install this command line tool, get a certificate, and use it in NFD or other NDNCXX based applications. I also have a standalone NDNTS personal certificate authority application. It can act as your personal certificate authority. You can use that app to obtain a main certificate from the existing Testbed NDNCERT legacy version. Then you can use that to issue sub-certificate to all your devices, and the issued sub-certificates will be published from an embedded repo in the personal CA app. This is a demo of the NDNTS personal CA and the command line tool. They are running in different machines. The personal CA is already configured with a certificate from the testbed. And then in the command line tool, I request the certificate from this personal CA using NDN certificate management protocol. As you can see, the P number showed up in the personal CA side, and then I type in that P number in the command line tool. The command line tool side obtains the certificate, and it's also installed into NDNCERT keychain, so you can use it with NFD. Another application I have is the home surveillance camera. I demoed this in NDN Community in 2018, but that version was based on NDN.js. But now I have rebuilt it with NDNTS, and also added a feature to share your screencast. So you can do screen sharing with this app. There is still no sound, and there is only 1 frame per second. This is the current limitations. I'm working on it. The way it works is similar to the previous version, but there are some differences. So if you select share a stream, you are the producer. You can use either the camera to capture your beautiful face, or you can select the screen to capture a window on your screen. It gets rendered into a WebRTC video element on the web page. Then it gets captured in a canvas HTML element as a JPEG image, which is then served as a segmented object. It also has RDR protocol internally. And then to serve anything on the NDN testbed, you need to do prefix registration. But the previous version has some very hacky way to do prefix registration, but now the registration command is generated in the browser itself. After asking for a certificate from the personal CA I deployed on one of my servers. Then if you select view a stream, you are the consumer. The consumer will just fetch segmented object from the producer, and then display the JPEG image in the HTML image tag. This is how the viewer looks like with my smiley face. And you can try this application using this URL homecam.ndn.today. Yes, it's online right now. You can try it. I hope this is enough to inspire you to start coding with NDNTS. The best place to get started is the NDNTS homepage available on my website. On my blog, there is also get started tutorials I posted 2 so far. And if you need API documentation, they are available in Visual Studio Code IDE or any other code editors after you install the library. Thank you for your attention.